A freight train weighing more than 15,000 tons is slowly moving toward another train. Together, that is over 30 million pounds of rolling steel. And somehow, the entire impact is controlled by one small metal device weighing less than 85 pounds. No computers, no remote control systems, no workers standing between the cars guiding the connection. The trains simply roll together. There is one loud metallic clang, and suddenly hundreds of tons become perfectly locked together. It sounds impossible, because the forces involved are enormous. During coupling, the impact force can exceed 400,000 pounds. That is enough energy to crush vehicles, destroy structures, or seriously damage cargo. Yet this tiny mechanical system absorbs those forces over and over again, every single day, in rain, snow, extreme heat, and freezing temperatures. And here's the crazy part. The basic design behind modern train couplers is more than 150 years old. Even today, one of the most important systems keeping freight trains connected across America still works mostly through pure mechanical engineering. No advanced electronics controlling the lock, no complex automation systems, just gravity, momentum, steel, and brilliant design. But the story behind this invention is much darker than most people realize. Before automatic train couplers existed, railroad workers had to stand directly between moving rail cars while trains rolled toward each other. So how did railroads solve one of the deadliest problems in transportation history? How can such a small device survive forces generated by entire freight trains? And why has almost nobody managed to improve the design after all these years? Before we dive deeper, make sure to like the video, subscribe to the channel, and turn on notifications. Because once you understand how train couplers actually work, you will never hear that metallic train clang the same way again. And trust me, what is happening inside that small piece of steel is far more sophisticated than most people imagine, because hidden behind every freight train connection is one of the greatest mechanical engineering designs ever created. So how does it actually work? And why did it completely change railroads forever? Let's find out. Today, when freight trains connect together, the process looks almost effortless. Two rail cars slowly approach each other, there is a loud metallic impact, and suddenly the connection is complete. The cars lock together automatically in just a few seconds. But railroads were not always this safe. During the early days of railroading, coupling train cars together was considered one of the most dangerous jobs on Earth. Back in the 1800s, railroads used something called the link and pin system. It was primitive, slow, and brutally dangerous. Instead of automatic couplers, workers had to manually connect train cars using a loose metal link and a heavy steel pin. To make the connection, a railroad worker had to stand directly between moving rail cars while they rolled toward each other. As the cars approached, he would guide the metal link into position and drop a pin through the opening at exactly the right moment. If his timing was wrong by even a second, the results could be horrifying. During the 1870s, thousands of railroad workers were killed or permanently injured while coupling and uncoupling rail cars. Some reports estimated nearly 10 workers every single day lost fingers, limbs, or their lives performing this job. What made it even worse was that railroad companies often treated these deaths as a normal operational cost. At the time, railroads were expanding rapidly across America. Freight traffic was exploding, trains became longer, heavier, and faster every year. Companies focused heavily on efficiency and profits, while worker safety remained a secondary concern. That meant railroad workers lived with constant danger. The average brakeman during the late 1800s reportedly survived only around 7 years before being seriously injured or killed on the job. The industry desperately needed a safer solution, and that solution came from a man named Eli Janney. Interestingly, Janney was not originally a railroad engineer. After serving during the Civil War, he later worked as a store clerk. But after witnessing the horrific accidents caused by the link and pin system, he became determined to create something safer. In 1873, he patented a revolutionary new design called the automatic knuckle coupler. The idea was brilliantly simple. Instead of requiring workers to stand between moving train cars, Janney designed a system where the cars could connect automatically when they touched each other. The coupler looked somewhat like two human hands clasping together. Each coupler contained a rotating steel knuckle mounted on a hinge. When two rail cars came together, the knuckles automatically closed around each other and locked into place. No worker needed to stand between the cars anymore. The impact itself powered the mechanism, and that single invention would eventually save countless lives. But surprisingly, railroad companies initially resisted the new design. Why? because replacing couplers across thousands of rail cars would cost enormous amounts of money. Even though workers continued dying, many companies delayed adopting the safer technology for years. Eventually, the problem became impossible to ignore. Public outrage grew. Railroad accidents continued making headlines, and finally, the United States government stepped in. In 1893, Congress passed the Railroad Safety Appliance Act, requiring automatic couplers on railroad equipment across the country. The results were dramatic. Within only a few years, railroad worker injuries and fatalities dropped massively. Some estimates suggest coupling-related deaths decreased by more than 60% after automatic couplers became mandatory. It became one of the greatest workplace safety improvements in industrial history. And remarkably, the core idea behind Eli Janney's original design still exists today. More than 150 years later, modern freight trains still use variations of the same automatic knuckle coupler concept. That alone tells you how effective the design really is. Because modern freight trains operate under forces that would destroy most mechanical systems almost instantly. Some freight trains stretch over 3 miles long. Many carry more than 200 rail cars loaded with coal, fuel, shipping containers, automobiles, or industrial equipment. A single fully loaded rail car can weigh nearly 300,000 pounds. And every time the train accelerates, brakes, climbs hills, or moves downhill, enormous forces travel through every coupler connecting those cars together. Some couplers experience massive pulling tension as locomotives drag the train forward. Railroad workers call this draft force. Other times, during braking or downhill movement, the couplers compress together under what railroads call buff force. And throughout all of this, the coupler must remain completely secure. No accidental release, no structural failure, no dangerous separation between rail cars moving at speed, but perhaps the most impressive part is this. Modern train couplers accomplish all of this using mostly pure mechanical engineering. No advanced computers controlling the lock, no electric motors forcing components into place. Instead, the system cleverly uses gravity, geometry, leverage, and momentum to make everything happen automatically. And once you understand what actually happens during the coupling process, you realize why engineers still consider it one of the greatest mechanical designs ever created, because hidden behind that loud metallic clang is an incredibly sophisticated engineering sequence happening in less than 2 seconds. And in the next part, we are going deep inside the coupler itself to see exactly how it works. At first glance, a train coupler looks simple, just a heavy steel mechanism mounted at the end of a rail car. But internally, it is one of the smartest mechanical systems ever designed. Everything begins with the knuckle itself. This is the large, curved steel piece at the front of the coupler that rotates open and closed almost like a human hand. Before coupling happens, the knuckle remains in an open position. As two rail cars slowly move toward each other, the angled faces of the couplers begin guiding themselves into alignment automatically. And this is extremely important because trains are rarely perfectly aligned during coupling. Tracks flex slightly, rail cars shift side to side, and couplers themselves can move several inches in different directions. Yet somehow the design naturally centers itself during impact. As the moving train car touches the stationary one, the collision force rotates the knuckle closed. The two knuckles wrap around each other, creating the mechanical connection. Then something incredibly clever happens. A heavy internal locking piece called the lock block immediately drops downward using gravity alone. Once it falls into position, the knuckle cannot reopen accidentally. No electricity, no hydraulic systems, no motors. Gravity itself locks the train together, and the entire sequence happens in less than a second. But the coupler does much more than simply connect rail cars. Behind the visible knuckle assembly is another critical component called the draft gear. This system absorbs the enormous impact forces generated during coupling. Remember, even low-speed coupling events can create forces exceeding hundreds of thousands of pounds. Without protection, those impacts would damage cargo, crack steel frames, or violently shake the entire train. The draft gear solves this problem by acting like a giant industrial shock absorber. Inside are powerful springs, friction plates, and energy-absorbing components designed to compress under load. During impact, the draft gear compresses several inches, converting kinetic energy into heat through controlled friction. This cushions the collision and protects both the train cars and the cargo inside them. But trains constantly experience changing forces even after coupling is complete. When locomotives pull forward, the couplers experience tension forces. When trains brake or travel downhill, the couplers compress together, Without damping systems, the entire train would jerk back and forth violently like an accordion. The draft gear smooths out those forces continuously while the train moves, and mechanical connection is only one part of the process. Modern trains must also connect their braking systems automatically. This happens through flexible air hose connectors commonly called glad hands. When train cars couple together, these air hoses align and seal against each other automatically. Once connected, compressed air flows throughout the train's brake system. This allows one engineer inside the locomotive to control brakes across hundreds of rail cars simultaneously. Passenger trains and some advanced freight systems also include electrical connections. As cars couple together, electrical connectors align automatically, allowing power, communication signals, and control systems to flow throughout the train. And despite the extreme forces involved, modern couplers are incredibly reliable. Many remain in service for decades with minimal maintenance. That reliability comes from the design philosophy itself. The coupler does not fight physics. It works with physics. It uses gravity instead of electronics. It uses momentum instead of external power. It uses geometry instead of complex alignment systems. That simplicity is exactly why the design has survived for more than 150 years. Countless engineers have tried improving it. Different countries developed alternative coupler systems. Some introduced more advanced features, while others focused on passenger rail applications. But for heavy freight trains, the classic knuckle coupler remains one of the most dependable systems ever created. And honestly, that says a lot about great engineering. Sometimes the best design is not the most complicated. Sometimes the best solution is the one that keeps working reliably for generations. Every freight train crossing America today depends on these couplers functioning perfectly. Hundreds of connections, millions of pounds of cargo, and enormous forces, all relying on a mechanical system invented in the 1800s. That is the hidden beauty of railroad engineering. Not flashy technology, not giant computers, just absolute reliability. And once you understand what is happening during every metallic train clang, you realize you are hearing far more than steel hitting steel. You're hearing one of the greatest mechanical engineering inventions ever created. Before this video, most people probably never thought twice about train couplers. They are small, dirty, covered in grease, and hidden beneath massive freight cars. But behind that simple chunk of steel is one of the most important mechanical systems in modern transportation. Every day, freight trains move billions of tons of cargo across thousands of miles. Food, fuel, automobiles, construction materials, electronics, and countless products all depend on these connections holding perfectly under enormous forces. And the amazing part is this: the core design solving that problem is more than 150 years old. That metallic clang you hear at railroad crossings is not just noise. It is the sound of gravity, momentum, steel, and engineering working together exactly as intended. It is also the sound of a safety invention that saved thousands of lives. And honestly, in an age filled with complicated electronics and advanced automation, there is something fascinating about a purely mechanical system remaining almost unbeatable after all these years. Before you leave, make sure to like the video, subscribe to the channel, and turn on notifications for more engineering and infrastructure documentaries like this one. And if you have ever wondered how massive locomotives generate enough power to pull mile-long freight trains, you should definitely check out the next video. Also, if there is another engineering system, machine, or hidden technology you want us to explain next, comment below and let us know. Your comments truly help support the channel and inspire future videos.